Section 5.4, Comparison Tests. This is from OpenStax Calculus Volume 2. At the bottom of every page there's a link. I would suggest you go there to download the full textbook. These videos are meant to supplement what's there to help those work together. So use them both. Alright, so in previous sections we discovered there are two classes of series: geometric series, which are of the form AR to the N, and P series, which are the sum from 1 to infinity of 1 over n to the p. And we know when these series converge and when they diverge. Okay, so this converges. These always converge if the absolute value of r is less than 1. And they diverge if the absolute value of r is greater than or equal to 1. That is worth knowing. And P series, we know that these converge. They converge whenever P is greater than 1. And they diverge when P is less than or equal to 1. So we can use those facts to our advantage by using the comparison test. So the comparison test, there are actually two tests in this section: the comparison test and the limit comparison test. This first one is often called the direct comparison test as opposed to the limit test. And what it comes down to is an idea from functions, from the sandwich theorem, or the squeeze theorem. So if we had two functions, okay, and we know that one of them is below the other. So in this case, my an is the lower function and my bn is the upper function. If I know that that one of them, an, is less than or equal to bn, and I know that bn converges as a series here, then an also has to converge. It's being pushed down. Okay, and they're both greater than 0. That's worth noting. It's squeezed between 0 and bn, so therefore it must converge. If, however, we know that bn diverges, okay, so still an is squeezed between 0 and bn. If an diverges, so I'm just going to draw this with an arrow here. If this diverges, then that forces bn to also diverge. Okay, so that is if there is some point where they are bounded this way, where an is stuck between 0 and bn. If there's some point that after that point that is the case, then this helps greatly. We can say if we know something about one, that tells us something about the other. So let's begin with number 36 here. Determine whether the series converges or diverges using the direct comparison test. Well, we can compare this to a P series. Okay, this is less than or equal to the sum from 1 to infinity of 1 over n cubed. And this is true for all n greater than or equal to 1. And it is, in fact, less than. So we can go ahead and say less than or equal to. But because that is true, we know, so since the sum from 1 to infinity of 1 over n cubed converges, we know that the sum from 1 to infinity of 1 over n cubed plus 3n plus 1 converges as well. Because it is less than that other one, for all terms, it converges. All right, let's look at number 37. Determine whether the series converges or diverges using the comparison test. All right, now this one, 1 over 2 to the n plus 1, is not of the form of a P series. Okay, we don't have n cubed and squared and anything. So let's try comparing it to a geometric series. Okay, let's compare this to 1/2 to the n. Or if you would prefer, 1 over 2 to the n. That is in fact less than that. It is less than or equal to 1 over 2 to the n. And that is for n greater than or equal to 2. No, actually this one is true at 1 as well. Okay, and again, this is just strictly less than. All right. The sum from 1 to infinity of 1 over 2 to the n converges. Therefore, sum from 1 to infinity of 1 over 2 to the n plus 1 converges. So we can compare it to a geometric or a p-series. All right, now number 38, same idea, the direct comparison test, starts at n equals 2 and goes to infinity. We have very few that actually don't start at 1, but this one starts at 2 because of the natural log. If it started at 1, it would be dividing by 0. So it does not look like either the geometric or the p-series. But let's notice that for n greater than or equal to 2, ln of n is less than or equal to n. It is less than or equal to n, which means that 1 over natural log of n is greater than or equal to 1 over n for all n greater than or equal to 2. So let's go ahead and try this. 1 over natural log of n is greater than or equal to the sum from 2 to infinity of 1 over n. Since the first term, well, n equals 1 to infinity diverges certainly from 2 to infinity diverges for 1 over n. This is the harmonic series after all. Since this diverges, the sum of n equals 2. I need to try to write those slower, I guess. From 2 to infinity of 1 over natural log of n diverges. Because it's greater term by term, it's certainly the sum is going to diverge as well. All right, determine whether this series converges or diverges. All right, same setup. Let's see if we can compare this to something. All right, well, I can definitely pull the same trick that we did last time, or a couple of these ago. The sum from 1 to infinity of n over n cubed. Okay, that is definitely true for all n greater than or equal to 1. But then this is also equal to the sum from 1 to infinity of 1 over n squared. And that's just true in general. I can cancel that. Now, because that's true always, this series, okay, since the series n equals 1 to infinity of 1 over n squared converges, right, that means that the sum from n equals 1 to infinity of n over n cubed plus n plus 1 converges, because term by term, it is less than or equal to what we have now determined converges. So if we can somehow compare it to a p-series or a geometric, that is fantastic. Those are the only ones that we really are completely familiar with at this point that converge at some point. So the comparison test is great if we have a series we know and we want to find something out about the series we do not know, whether it diverges or converges. Let's consider this one right here. Example 40, the sum from 1 to infinity of 1 over n squared minus 1. All right, well, I would love to say that 1 over n squared minus 1 is less than or equal to 1 over n squared. That would be great if we could say that it's less than that because this converges. because it converges, that'd be great. Well, that is not true. So it is actually greater than a converging sequence. So therefore, the series is, there's nothing, we can't say anything about that. That is not helpful. All right. Next, let's say, what if that is, wouldn't it be great if that were greater than 1 over n, because 1 over n diverges. That's not true either. Okay, that is less than or equal to, or strictly less than, but that doesn't help. Okay, so we cannot apply the comparison test. We just can't do it. But if we compare the terms of 1 over n squared minus 1 to 1 over n squared, if we compare them term by term, then we end up with something like this. This would be the limit. Okay, and n goes to infinity of 1 over n squared minus 1 divided by 1 over n squared. Okay, which is n squared over n squared minus 1, and that limit goes to 1. Now, what does that tell us? It says that they grow at a similar rate. The rate of increase is the same for both of them. So that actually means that if the sum of an, or if sum of bn, in this case, this sequence converges, then that means that this sequence also converges. And that is where the limit comparison test comes in. Okay, so let's first just say we've got these two sequences. Both of them are greater than or equal to 0 for all n greater than or equal to 1. If the limit, now these are term by term, if an over bn, we're kind of disregarding this fact that they are series, we're looking at the sequences that make up the series. If an divided by bn goes to a number, if the limit is L, where L is not 0, then they either both converge or both diverge. We use that fact in the last example because 1 over n squared converged, so therefore they both converged. If the limit of an over bn is 0 and bn converges, then that means that an converges. Likewise, if an over bn, if that limit is infinity and bn diverges, then that means an diverges. Okay. Now this can be inconclusive. We can come up at the end and say we don't really know. Okay, that can happen. And it does occasionally. So let's look at 41. Determine whether the series converges or diverges using the limit comparison test. All right, well, for my sequence an, that is 1 over square root of n plus 1. No square root there. All right, the sequence bn, what we're going to compare it to, well, why not 1 over the square root of n? Because that is a p-series, and it diverges, because the p value there is 1/2, which is less than 1. So let's go ahead and take the limit of these two. All right, 1 over square root of n plus 1 over 1 over the square root of n. That is the square root of n over the square root of n plus 1. And that is 1. Okay, that limit there is 1. Which means that is not 0. So they either both diverge or both converge. This diverges. Okay, so by the limit comparison test, we can say that the sum n equals 1 to infinity of 1 over square root of n plus 1 diverges. And it's important to take stock at the beginning whether that diverges or converges, because that will help you make a determination. Because you always want to look back at those three conditions and say which one of these actually applies. And there's the link to check out this textbook. You should do that completely. All right, now let's compare this series. All right, so our an sequence is 2 to the n plus 1 over 3 to the n. Now we want to pick a sequence bn that we know whether it diverges or converges. All right, well, this actually looks like a geometric sequence. So let's go ahead and choose 2/3 to the n. Now here the r is the ratio of 2/3 is less than 1, so this one converges. Now let's consider the limit of an over bn, which is 2 to the n plus 1 over 3 to the n, all over 2 to the n over 3 to the n. Right, so taking the reciprocal there, we actually get 2 to the n plus 1 over 3 to the n times 3 to the n over 2 to the n. Okay, rearranging that, we get 2 to the n plus 1 over 2 to the n. Okay, which is equal to 1 plus 1/2 to the n. That second term goes to 0, so the limit here is 1. Okay, now our bn, well actually that doesn't matter what happened to that, because this limit is 1, which is not 0, then they both converge or both diverge. Since bn converged, we can say the sum from 1 to infinity of 2 to the n plus 1 over 3 to the n converges by the limit comparison test. All right, next, 43. We have got the natural log of n over n squared. Okay, very similar to something we had previously, ln, or 1 over ln n, and then we compared that to the harmonic series. We have a ln of n over n squared. First, let's take bn equal to 1 over, why don't we start with n squared? Let me try that, see what happens there. You never know what's going to happen. All right, so we will take the limit as n goes to infinity of ln n over n squared over 1 over n squared, which is the limit as n goes to infinity of natural log of n. All right, that is infinite. All right, so looking back, if we have infinity and bn diverges, now we should probably note that our bn converges. So that's inconclusive. Okay, choosing bn equal to 1 over n squared yields us something that's inconclusive. Let's try again. bn equals 1 over, why not 1 over n? All right, so that's something we know diverges. All right, well that would be the limit as n goes to infinity of natural log of n over n squared divided by 1 over n. And that is going to be, if we rewrite that, that is natural log of n over n. Right, applying L'Hopital's rule to this, okay, because these are continuous functions, just functions in terms of n, that would be 1 over n, which is 0. Okay. If our limit is 0 and bn converges, bn diverges, okay, that's inconclusive again. That does not work. Let's try again. It's still, because of that n squared, it appears something's going to work. So let's try something right in between those two. 1 over n to the 3 over 2. Over n to the 3 halves. Okay. Now, we do know that this converges. Okay, because it's a p-series with p equal to 3 over 2. So we've got converges, diverges, and we ended up with 2 inconclusives. So let's try again. This will be the natural log of n over n squared over 1 over n to the 3 over 2. That is equal to the limit to infinity of natural log of n. Okay, and that will be a negative 1/2, so we'll have the square root of n. Alright, let's attempt to take L'Hopital's rule here, because that is infinity over infinity. Okay. L'Hopital's rule tells us we have a limit of 1 over n over, derivative of that is 2 square root of x, or 1 over 2 square root of n. All right, algebraically, that is equivalent to, let me flip that, we get, let's see, we'll get a 2 over the square root of x, or 2 over the square root of n, rather. Okay, which that equals 0. Okay, now if our limit equals 0 and Bn converges, it does, then An converges. So by the limit comparison test, n equals 1 to infinity of natural log n over n squared converges. Okay, I said at the beginning, this can happen, and it does, where you try once, you try twice, you try 3 times, and nothing works. You just sort of have to play with it. Now, the good news is we were told to use the limit comparison test. If we hadn't been given a test, we have several other things we can try. And at the end of this chapter, we'll kind of discuss a flow of what makes sense to try when. Now, lastly, we will use this one, 5 to the n over 3 to the n plus 2 using the limit comparison test. Now, this appears to match up with one of our geometric sequences. So Bn will choose 5/3 to the n. Now that diverges. That diverges because 5/3 is greater than 1. So let's compare these two, again, term by term. So we have 5 to the n over 3 to the n plus 2 over 5 to the n over 3 to the n. All right, let's see, that will be 5 to the n over 3 to the n plus 2 times 3 to the n over 5 to the n. And that limit, once we rewrite that algebraically, that is 5, 3 to the n over 3 to the n plus 2. That limit is 1. Now, if the limit is not 0, but it's a constant, then they both converge or both diverge. So by the limit comparison test, since the sum from 1 to infinity of 5 over 3 to the n diverges, the sum from 1 to infinity of 5 to the n over 3 to the n plus 2 diverges as well. All right, that brings us to the end of this section. There is the limit comparison test and the direct comparison test. Be careful when to use which one. Oftentimes, the limit comparison test actually is a little more beneficial. So, that's it.